In the first video, we created a graphical window using STL. In this video, we see how we can draw onto it. And as an example, we're going to create this pattern that you see here on the screen. So let's get started. It might seem that the way this works is that there's some API that we call that lets us change the color of each pixel. But that would be very slow because you need hundreds of thousands of calls to just create one image for one frame. So the way this is usually done is that we create the image in RAM and then tell STL to put it on the screen with one or two calls. So our first step is going to be creating the image in RAM. And to create the image in RAM, we need some memory to store the colors of the pixels, Framebuffer. So we need to know how much memory we need. And that depends on our window dimensions that we have passed here to the create window. So let's pull them out so that we can use them in other parts. And so now, according to STL's documentation, the window that gets created might have different dimensions, and the reason is that, I don't know the reason, but I think on some high density monitors that this might happen. So it recommends that we query the size of the window after it's created. So I'm going to do that using a function called STL get window size in pixels. And this function, first you pass the window and then the address of the variables for width and height that you want to get filled. So that's it. So now we have the correct dimensions of our window. It's time to, now we can go and create memory. I'm going to use malloc. And malloc takes one argument, the number of bytes that you need. And since we need this memory to store the colors of pixels, the amount of memory we need depends on how many pixels we have and how much and how many bytes we need for each pixel. And the number of pixels is easy. It's just for our window is a grid of pixels. So window width times window height. And now, how many bytes do we need for each pixel? Each pixel has 3 colors, red, green, blue. So 3 bytes, because we're going to use 1 byte for each of them. But I'm going to use 4 instead, because CPU can write a 32-bit int faster than 3 separate bytes for each color. So we use 4. And we're going to put this 4 in a variable too. Let's call it bytes per pixel. And malloc returns a void pointer, but I'm going to cast it to an int pointer. Because as we talked, each of our pixels is going to be an int. So this way, it's like our memory is just an array of pixels. And that would be very easy to select a pixel by just indexing the array, as we'll see later. So I'm going to call this pixels. And that's it. We have created memory for pixels. One thing is missing. I mean, there's one thing that we need to know. What's the order of the pixels? For example, the first int in the buffer, which pixel on the screen is it going to correspond to? And the answer to that comes from this picture. Imagine that this is our buffer and this is our screen. So our screen has 3 rows, each of them 4 pixels. Then STL is going to map the first bytes in the array to the top row, and then come the pixels of the row below that, and so on. And as you can see, the order for each row is from left to right. So with that in mind, we can come down here and start looping through our pixels and set their colors. Now we can write this loop any way you like, but to keep the calculations for the indexing simple, it's better to start to loop for each row and then each column from top to bottom, left to right. So I'm going to write that. And now we've written the loops, and now we can select a pixel by just indexing it. I write the formula and then I explain it. I explain this with an example. Imagine that this is our screen, and as you can see, it's 1,000 pixels wide. Now let's talk about this pixel here. Let's calculate its position in the buffer and then see if this formula calculates the index correctly or not. Now, because of the way STL maps the buffer to the screen, this pixel is going to be the first in the buffer. This is going to be the second, and we go, and here we get to 1,000, then 1,001, 1,002, 2,000, 2001, and this is the position 2005 down here. So this is going to be 2005. Now the indexes start from 0, so 0, 1, and the index for this pixel is going to be 2004. And now let's calculate the formula. Calculate the index using the formula. As you can see here, we have our row and column starting both from 0. And as I said, we're going to assume that we're going top to bottom and left to right. So the index here is going to be 0, 1, 2. And the index of the column is going to be 1, 2, 3, 4. So the index for row is going to be 2, width is 1,000, column is 4. So that adds up to 2004 as we expected. So now we have selected a pixel. We have to set its color. The colors are red, green, blue. I write 3 variables for them separately and handle them separately, and then we combine them and put them in the pixels here. Each of the colors is going to be 1 byte from 0 to 255. So it should be unsigned. And we can use unsigned char, but it's shorter to just write uint 8t. This is from the standard library. It's included in the stdint header file, but we don't need to include it here because STL already does that. So we're going to have 3 of these for our colors. So what should the formula be for each of them? Well, it depends on the pattern that we want to create. This is the image that we're going to create. And this image is created by setting the red channel of the pixels on the left to 0 and gradually increasing it to 255 on the right. And the same for blue, it starts from 0. This is not blue, this is green. To start from 0 on the top and increase it to 255 at the bottom. And then the blue is set to 0 everywhere. And as you can see, this corner is black, and the reason is because it's both on the left and on top, so both red and green is 0, and blue is always 0, so that's going to be black. And here, since both red and green are at their maximum, we have yellow because red and green combined produce yellow. So now what should the formula be for red, for example? Well, red, as I said, starts from 0 to 255. And I'm going to write it 255 times a ratio. And that ratio is going to start from 0 when our column is 0 and go to a maximum of 1 when we're totally on the right and our column is window width, almost. So what should it be? Column divided by window width. And we just need to make this float, cast it to float before we do the division. Otherwise, we get an integer division, which results in 0 because column is always less than window width. And we do the same thing for green. The only difference is that we use the row and the height, the window height. And as I said, blue is going to be 0 all the time. Okay, now that we have set the colors, we need to put them together in the pixels. And if you remember, I said that our pixels are just ints, so there are 4 bytes. And we have to put the 3 bytes of the color here. Now, there is no rule that says what the order should be, but whatever we decide here, we have to remember it so that later we tell STL about it. I'm going to use the RGB for the 3 colors. And the last one, it's empty, but the way I'm going to use it is STL is going to interpret it as alpha, which controls the transparency. And we'll see how this works in a second. So how are we supposed to put the 3 bytes here in this pixel? We do that in 2 steps. Imagine that these are bytes for the colors. In the first step, we need to turn each byte into a 32-bit int with the color in the right place. For example, for the red byte needs to be here, and we need 24 zeros here. And the green should be here, and so on. Obvious, right? And the next step is going to be combining these and producing this value, this pattern here, and so that we can put it in the pixel. Now let's talk about the first step, turning the bytes into a 32-bit int with the color in the right place. For that, we use an operator called left shift, and this is the operator. And the way it works is that when you apply it to a byte, at least in this case, it's going to turn the byte into a 32-bit int with 24 zeros on the left, and then it's going to shift the bits to the left and put zeros in their place. So, for example, in this example, we have 10. So these bits are going to be shifted to the left, and 10 zeros appear here. So this is what left shift does. So with that, this is like this value here is just red shifted 24 bits to the left. And this one is green shifted 16 bits. And the same for blue. So that was the first step. The second step, as I said, is combining these values and putting them and producing this. For that, we use another bitwise operator called the OR, or bitwise OR. And this is the way it's written. And when you apply two operands, for example here, X and Y, it's going to look at X and Y as just strings of bits. And then it's going to combine them and produce another bit pattern by just looking at each position. And in each position that both the operands have a 0, it produces a 0. And when one of the operands has a 1, it produces a 1. So when you apply this left shift to these values here, we get the red values, the red color here, because these are all zeros, and we get this. So let's write that in our code. Now there's one more step, one more thing that we need to do. Right now, the way we've done this, we have 0 here. And as I said in this slide here, the way I'm going to do it, STL is going to interpret this part, the last byte, as the alpha, which controls the transparency. And 0 means fully transparent. So that way, this image, the color won't appear because it would be transparent. So instead, we need to turn this to maximum, which is 255 for a byte. And for that, we use the OR operator one more time and produce this. So we OR this with 255, and this is the bit pattern for 255, and this is what we get. Okay, now that we have created the image in RAM, we're going to put it on the screen using STL. And we do it in 2 steps. The first step is going to be creating something called a texture, which is kind of like a memory on the GPU for images. And then we put the texture on the screen. So for the first step, we come here, down here, right after creating a renderer, we create a texture. And the function for creating a texture is called createTexture. First, you pass the renderer and then the pixel format. And if you remember, we decided that our pixels are going to be RGB and then A. So we use STL (8) is the number of bits. And there is something else called RGB-A32. It's similar, but there's a small difference. I'm not going to explain it here why. It has something to do with the Indianness of the computer. But if we write the 32, things will not work properly here. So I use the 888. The next argument is texture axis. It's not very important, but STL is going to use that just for optimizations. And since we're going to update our texture every frame, we have to pass something called STL texture axis streaming. And after that, the width and height of our texture. And since our texture is going to be as big as the screen, we just pass the window width and height. createTexture is going to return an STL texture. And now after creating our texture, we come down here right after updating our pixels each frame. We're going to update our texture using the pixels. So we just tell STL to copy this pixel, this image that we created in the RAM on the texture. And for that, we use the function STL update texture. The first argument, the texture. The second argument is used when we want to update the part of the texture. We don't want to do that, so null for all of it. And then pixels. And the last argument is going to be the pitch. Pitch is the number of bytes in each row of our buffer. So the number of bytes in each row is just the number of pixels in each row times bytes per pixel. So now the texture is created. All we have to do is to put it on the screen using render texture. The first argument is the renderer, then the texture, and the last two arguments are when you want to put part of the texture on part of the screen. We don't do that. So now if you press F5, okay, it's just a typo. So let's come here, pixels, and here's the image. So thanks for watching. The next episode is going to be about the algorithms for drawing a line. We'll see. Bye.